So hello everyone, my name is Ying, and in this talk I will talk about left-orderability of three manifold groups and the foliations of three manifold. So basically I will try to give you a very brief survey on results one can get about left-orderability of three manifold groups from using so-called universal circle actions. So those are actions of pi 1 of M on circle constructed from foliations on your manifold. So foliations here will include both codimension 1 foliation as well as dimension 1 foliation, which will be flows on your manifold. So most part of this talk is part of joint work with Steve Boyer and Cameron Gordon. The talk consists of two parts. Part 1, I will just trying to explain what are those universal circle actions and kind of roughly how you can get this type of action from foliations on the three manifold. In the second part, I will present some results we get by applying those circle actions. So first, let me just remind you what is the L-space conjecture. If M is an irreducible rational homogeneous sphere, then the conjecture says pi 1 of M is left-orderable, is equivalent to M admits a co-orientable tau foliation, as well as M is not a Hager floor L space. So a rational homogeneous sphere is an L space if the dimension of the half version of the invariant is minimum. That just means it is actually equals to the first homology of the manifold itself. So if you look at this conjecture, in one way it says if your group admits some very nice linear order, or the manifold itself admits some very nice decomposition, then the full homology of the manifold should not be very simple. Among all of those directions, there is one direction is known, that is 2 implies 3. So if you do have a co-orientable tau foliation, then M indeed cannot be a Hager floor L space. This was originally proved by Orzabal for say 2 foliations. And then there is this crucial step in the original proof, which was later on established independently by Jonathan Bowden and Will Kazaz, Rachel Roberts for say 1,0 foliations. Okay. And by the way, so you can say in this talk, we are basically trying to explore, how to show pi 1 of M is left-orderable from co-orientable tau foliations, as well as, transverse flows. So let me just start with defining what is a left-orderable group. So a group is called left-orderable if there exists a straight total order. That means you can compare any two elements inside the group. In a way, this ordering is invariant under left multiplication. So intuitively, that just means if you think about the group is just a collection of elements, then when you introduce any linear order, roughly speaking, you'll be able to place those elements along a real line with respect to this linear order. And if your order is actually left order, then when you're looking at the group action on itself by left multiplication, then the action will just appearing to be translation since the order is preserved. And let me give you two quick examples. The first one is a group of integers. This is obviously left orderable, and then the order you are using is just the usual order. The second example is none of the finite groups is left-orderable. This is also very easy to say because if your group only have finite number of elements, then with respect to any linear order, you are going to have a maximum. And if that linear order is left order, then the maximum is going to be preserved under the group action, which is a contradiction because the group action itself does not have any global fixed point. Okay, so we all know three manifold groups are very special in terms of left-orderability of the three manifold group. We have this really useful theorem by Boyer, Rolfson, and Wist. It says M is irreducible orientable, then pi 1 of M is left-orderable if and only if there exists a non-trivial action of pi 1 of M on the real line. There is a similar statement for countable group like this in general, but there you would require the action to be faithful. So you can see here for three manifold group, the requirement of being left-orderable is already relaxed dramatically. But even so, in general, it is still really, really difficult to directly produce a non-trivial action on the real line, which leads to the next slide. We actually have a lot of examples of pi 1 of M acting on S1. The first set of example, which I'm not really going to talk about, is the linear representations of pi 1M goes to PSL2R. So PSL2R acting on RP1, which is a circle. If you go to Xinhua Gao's talk, then she's going to talk about that a lot. So in this talk, we are going to mainly use the second set of example. They are called universal circle actions. There are a lot of universal circle actions, and let me just go through some of those. The first one we are going to use is coming from top foliations. So you are going to require top foliation to have hyperbolic leaves. And just to make a really quick remark here, if your three manifold is actually rational homologous sphere, then any transversely orientable top foliation will satisfy this property. That's essentially because if there's any leaf which does not grow exponentially, then that will produce a non-trivial element in the second homology class, which contradict to the fact your manifold is rational homologous sphere. Okay. And then the second set of example we are going to use, second construction we are going to use is from pseudo-Nassau flow. I'm going to explain what pseudo-Nassau flow is roughly, but this is constructed by Finlay. There are another two, I'm just going to quickly mention it, and we're not really going to use it. That is in the very same paper by Danny Caligari and Nathan Dunfield, where they construct the universal circle action from top foliations. They also have another construction which give you the circle action from essential laminations. So those essential laminations need to be very full. That means if you're looking at the complementary region of the lamination, those complementary regions need to be suspension of ideal polygons if your manifold is closed. Okay. And then lastly, there is also a type of flow called quasi-geodesic flow. That means if you look at the lift of the flow line in the universal cover of a hyperbolic three manifold, they are actually quasi-geodesic. And it turns out you can also construct some universal circle action from this type of flow. But again, we're not going to use those two, so I just can't mention this so you know there are other type of constructions out there. Okay, before I even say, I will tell you a little bit more about those first two actions which we are going to use in showing the result. But before that, let me just quickly say this general thing. Just to remind you, in order to show three-manifold group is left-orderable, you need an action on R. So if you have an action on a circle, this is some standard obstruction, and it tells you the action on the circle can be lifted to an action on the universal cover of a circle, which is R1, if and only if the order class of the representation is equal to 0. So here the order class of the representation is an cohomology class in the second group cohomology. This is essentially because the second group cohomology with z coefficient is somehow parameterize the central extension of the group by z. I'm not going to say too much about this. You can find a little bit more detail, I guess, in my very first paper, kind of explain why this works. But here I just want to give you a quick example. So this example kind of will help you understand why the help you understand the order class of universal circle action as well. So here I'm going to take f is a closed surface hyperbolic. So if you're looking at the pi 1 of f acting on its universal cover, now it's just a copy of H2. This induces the action of pi 1 of f on the boundary of H2, which is a circle. You can ask yourself, what is this circle order class of this circle action? It turns out this is just the order class of the unit tangent bundle of the surface, which is inside the second group cohomology, which is identical to the second cohomology of the surface, since the surface is k pi 1 in this case. It's actually not very hard to say why this is the case. It's essentially because at every single point of H2, you given any direction, there is a unique geodesic, shooting to the boundary infinity, and that's give you a point on the boundary of H2. So in this way, you can identify the set of unit vectors and any point of H2 to the boundary of H2. And you are going to use the fact that the action is equivariant, and then cook up isomorphism between the unit circle bundle of f to the S1 bundle coming from this representation, and which will give you the fact their order class are the same. Okay, so now let me just go ahead and tell you what happened if your action is a universal circle action. How do you lift them? So that's depending on how you get the universal circle action. If the circle action is from a CTF, then it turns out the order class of that action is just equal to the order class of the tangent plane bundle of the foliation. So here your plane is tangent to the leaves of the foliation. So to summarize, that means if you have a co-orientable tau foliation whose tangent plane bundle has zero order class, which means it's trivial, that implies pi 1 of m is left-orderable. Then the second set is if the universal circle action is from pseudo-NASA flow, then the order class of the action is equals to the order class of the normal bundle of the flow. So again, that means if you have a pseudo-NASA flow on the three manifold and the order class of the normal bundle of the flow is equal to 0, then you can conclude that the pi 1 of the manifold is actually left-orderable. So this is essentially the two main ways we are going to show pi 1 of m is left-orderable. So for the remaining part of this talk, I'm going to trying to be carefully define what is topolation, what is pseudo-NASA flow, and give you one example what is a universal circle action looks like in that example. Okay. So topolation is a co-dimension one foliation on your three manifold. So that just means that you are going to decompose your three manifold as a disjoint union of injectively immersed surfaces. Those surfaces are called leaves of the foliation. And here my foliation is going to be C10. That means the leaves of foliation are differentiable, but the transverse direction is just continuous. That just another way to say this is the tangent plane bundle is defined, and it's C0 over M. Okay. There is this result by Danny Caligari. It says if you give me any topological foliation, that means the leaf may be just topological, it's not even differentiable, not even C1. But this result of Danny Caligari tells you can always isotopy a C0 foliation to a C infinity 0 foliation. That means the leaves actually can be isotopic to be smooth. Okay. So in that sense, we are really not losing anything by requiring my foliation to be C10. Then a foliation is called taut if there exists a closed transversal, that's a closed loop that and transverse to your foliation everywhere, and every single point of M. So in Kazaz and Roberts' paper, they call this everywhere taut. So basically, this is just to guarantee that every nice property of differentiable taut foliation still hold for C10 foliation if you insist there exists a closed transversal at every single point of your manifold instead of just for every leaf of the foliation. And so next look at pseudo-NASA flow. It's a type of flow on the manifold. So intuitively, you should think about points on your manifold is moving, and the flow line give you the trajectory of those points. And formally, a flow is a continuous R action on your manifold. That is just to say it's a homomorphism from R to homeo of M. A pseudo-NASA flow is a generalization of a NASA flow. So maybe I will just first tell you what is a NASA flow is. So if you have a NASA flow, then you can basically decompose the tangent bundle of your manifold as a direct sum of three line bundles. So those are stable direction, flow direction, and unstable direction. So that's ES and EU. By the way, ES and EU may not be trivial, so it may not be orientable. But regardless, locally, you can still just thinking about those directions like the eigendirections of the differential of phi t. So in that sense, let me see if I can write. So here, yeah, okay. So here, if you follow the flow line and looking at how the flow, acting on the normal direction, you have this stable direction where the vector is contracting, and the unstable direction where the vector is expanding. So locally, you should imagine the differential of the flow with respect to those directions is diagonal, kind of like lambda t 0, 0, lambda t inverse. Okay, it's like a hyperbolic behavior. And then you want this lambda t, depending on t in general, and you want it kind of like uniformly bounded away from 1. This is bigger than 1, but you want to be uniformly bounded away from 1. That's how you get this exponential growth right here. So if you look at the formal, more formal definition here, if you have a vector along the stable direction, then going forward, it will shrinking exponentially. And if you take a vector along the unstable direction, then it will expanding going forward exponentially as well. Okay, so this is basically the intuition of a NASA flow. And then for pseudo NASA flow, it's basically the same thing, but okay, I guess the pseudo NASA flow is essentially just a NASA flow, but away from finite set of closed singular orbits. So those singular orbits, you should kind of imagine locally the pictures looks like some type of branch cover of the flow line of a NASA flow. And again, if you look at this picture right here, oh, what happened? Okay. So if you look at this picture right here, if you look at just how this normal direction is, because it's kind of like a branch cover, so you're not just have like a one direction, stable, unstable, you have like multiple directions. So here I just draw the example. And obviously, this is not differentiable going along the singular orbits. If you are familiar with pseudo-Nassau map or Nassau map, then this is precisely the picture for pseudo-Nassau map at the singular points of singular foliations. Okay. So that's kind of hinted. The example I'm going to give it to you in the next slides is actually just a suspension flow of pseudo-Nassau homomorphism. So I'm going to use this example to kind of demonstrate where the universal circle actions are from. My M is going to be surface bundle over S1. So I will need the fiber to be hyperbolic and closed. And phi is the pseudo-Nassau. That's a monodromy. This is a map you use to identify the top and bottom of that thickened surface. So in this example, the co-orientable top foliation is just a fibration. Okay, so all the leaves are compact, and they just you can see the foliation easily. And the pseudo-Nassau flow is, as I mentioned before, it's just a suspension flow of phi, and it's a pseudo-Nassau basically coming from the properties of pseudo-Nassau map. Just to remind you again, the fibers are hyperbolic. So I do have, so going back here, I do have a CTF foliate, with leaves are hyperbolic. So when you look at the universal cover of those leaves, here is just the fiber, it's copies of H2. And I'm going to use phi delta to denote the lift of phi to the universal cover, which will induce a map of the boundary of universal cover. So that's a map from S1 to S1. In general, the universal circle action is induced by the deck transformation of pi1 on the universal cover of the manifold. So in this example, you are going to see in a minute, but I'm just going to write down the action here. That just, well, here because M is a surface bundle, so pi1 of M is an extension of the surface group. So depending on where the element is, if the element in pi1 is coming from the surface group, then the action on the circle is just the deck transformation. And if you are taking this another generator, which represented by a loop, intersect the fiber once, then the homomorphism of the circle is the induced by the lifting of your monodromy phi delta, as we described above. So this is a universal circle action, but I didn't tell you what universal circle is. So the last slide, let me just kind of quickly say that. Oh, what happened? Okay. Okay. Anyway, so let me just say this. So here I have my M, which is a surface bundle over S1, and this cylinder-looking thing is M delta, which is a universal cover. So let me just kind of demonstrate what happened if you have CTF and what is a universal circle. So when you have a CTF of hyperbolic leaves, this is leaves. So each leaf, in this case, is just a fiber were lifted to a copy of H2 in the universal cover. So in this example here, that just those are horizontal disks, right? Each of those is going to be a copy of H2. And then luckily for H2, you are going to have a boundary which is homomorphic to a circle. So here you are going to say, those are the horizontal circles on the boundary of this infinite cylinder looking thing. And then essentially the universal circle for CTF is from, so this is from the collection of the circles coming from the pullback of your leaf. And this I'm saying this is from, but this from is very, very complicated. But in this example, it's actually pretty easy because all of those circles coming from the pullback of a leaf, they are just nicely, on top of each other. So you essentially can just identify all of them by smashing them to this pink circle, and that's your universal circle. And if you're thinking about, if you just run through how pi 1 of m acting on m delta, and imagine how that induced action looks like on this pink universal circle here, you will see that is actually the action I gave it to you in the previous slides. Okay, so this is for CTF. And if you have a pseudo-NASA flow, then again, this is maybe I'll just write in green. So the green part is a flow line, and you are going to look at the pullback of the flow line. Okay, and then this is a result by Finley. I mean, everything, this whole thing is by Finley. It says the orbit space of the pullback flow, which just means the universal cover quotient the flow line. This is actually homomorphic to R2. And again, in this example, it's very easy to say because you can just kind of say here every single flow line is going to intersect this disk, which is bounded by this pink circle right here, once. And that tells you this disk right here is actually just the orbit space of the pullback flow. And another thing he showed is you can actually, compactify the orbit space by, this is, maybe I'll just use, so by a circle, which will give you a disk. Okay, and this circle is your universal circle coming from pseudo-NASA flow. And again, this is in this example, you actually just say because this is your orbit space, and this is going to be the circle you are looking at, and that's precisely exactly the same as the circle coming from this guy right here. Okay, So this is just like a toy example, but it kind of give you the idea, what other universal circle action are. So I think I will just stop here. This is going to be the end of the first part. And in the second part, I will just show you some result from applying those two type of circle actions. Okay.